Hello, I do. Hello. Hi, that's me. That's everybody else. Hi, everybody else. All right, we're gonna have fun with decimals. Oh shit. Hello. Okay. So, what does a decimal mean to you? Oh, no. And? What you said?
Yeah, so like $1.02.
Oh, like $1.02. All right. What else?
And the question was, what is a decimal?
What is a decimal?
So I
Yeah, go on.
I've got two answers that I think might work. Either a decimal is a fraction created of or from a whole number, though uses whole numbers to describe said fraction. And that's my idea on fractions. The other one is a decimal is a new placeholder for smaller numbers.
Placeholder or place value?
Well, I said placeholder.
Okay.
So it's
Sure,
really any place.
Placeholder. Place value for small numbers, is that what you said?
Smaller.
Okay, anybody else?
You want the real deal?
Sure.
Any number that is represented using place value and powers of 10.
Okay. Powers of 10. Okay, anybody else? Yes.
You know, if you're smaller than 0.
Smaller than 0. Between 0 and 1, maybe? Okay, could be. Between, all good ideas.
I'm suddenly curious though, because personally I don't feel that it should be powers of 10. Because what if you change the base? The decimal would still work. But like let's say base 12, base 4.
You can do decimals in base 12 and base 4, but you wouldn't really call them decimal because deci literally means 10. So our whole number is a decimal number system. What we're branching into now are decimal fractions, to be more precise. We call them decimals, but what we really mean are decimal fractions. Fractions, we mean part of a whole. Right? And we do have other powers of 10 to consider. So just go back to what we did before. Kids got used to for a while that we have thousands, right? And we have hundreds, and we have tens, and we have ones, and eventually they learn those are powers of 10. Right? 10 cubed, 10 squared. Oops, equal sign. 10 to the first. What's 1?
10 to the 0.
10 to the 0. And a cool thing about our number system is a pattern evolves from this. So on the left side, would you agree that I'm dividing by, whoa, that was crazy. That I'm dividing by 10 as I move down here? 10, divided by 10. On the top, I'm dropping the power by 1 each time. As I move down from the bigger powers of 10 to the smaller powers of 10. And it turns out that we can just keep going. So if I go 3, 2, 1, 0, what's the next obvious number? -1. So down here I get 10 to the -1. On the other side, I just keep dividing by 10, and so 1 divided by 10 I could say is 1/10. That's the fraction version. Humans have been doing fractions for thousands of years. We've only been doing decimals for a couple of hundred, at least decimal fractions. They haven't been around very long. And they didn't start off looking like that either. And we'll talk about why in just a minute. And so then we can just keep going. We drop the power again, that's 10 to the -2. What's 1/10 divided by 10?
1/100.
You know, to double check, 1/10 divided by 10. Our rules for working with fractions are division is multiplying by the reciprocal. So that would be 1/10 times 1/10, and there's my 100th. Cool. And we've learned this abbreviated version where you put a 0.01. Now, I like to put the 0 to the left of the decimal point, just to be clear on some things. Like, I hate it when I have something like that written on a paper and I don't see the dot there and I think it's 1 instead of 1/10. So I usually put a 0 in front of it to be clear. Because I wouldn't write 0,1 when I mean just 1. Okay. So let's look at our number system in a slightly different way, and we'll come back to this. So, we have our 1s, we have our 10s, we have our 100s, and so on. And then going the other way, we have our tenths. We have our hundredths. And so on down the line. Now, do you guys see like some symmetry going on here? Where's the point of symmetry when I write them out in words like that?
When you go 100ths ones, it'd be 100 ones, 10 ones, and then 1/10, 1/100.
Say that again? What's the point of symmetry? That's what I want to know. That's some
sounds-
symmetry, right?
The ones and the tens.
Between the 1s and the 10ths, there's the symmetry? Well, is there a 1ths place? No. So really the symmetry lies around the 1s. The 1s is kind of the middle when we start throwing decimal fractions in with the regular decimal base 10 stuff. Right? And think about the powers of 10 that I'm playing with here. That's 10 to the first power. Oh, oops, that's over here, 10 to the first power. This is 10 to the 0 power, right? This is 10 to the second power. This is 10 to the -1. This is 10 to the -2. Right? We still have that symmetry. The balance point here, where we're symmetrical around, is the 1s place. Now, we got used to putting a decimal point right there between the 1s and the 10ths. Okay, and that separates the whole numbers from the fractional numbers. Okay, that makes sense, whole numbers, fractions. But really, another way to think about the number system is that the 1s are kind of the middle of the way we write our numerals, and then we have an equal distribution on each side. We have 10s on one side, 10ths on the other, hundreds on one side, hundredths on the other, thousands on the left, thousandths on the right, balanced on each side. And that's a good thing to emphasize to kids, because sometimes kids get confused about the decimal places. They kind of want there to be a 1s place. They want the same stuff on the left of the decimal to be on the right, and that causes some confusion at first. And sometimes that confusion is never addressed, and they know the place values, but every once in a while that misconception early on comes up in somebody's head and screws stuff up. And I've seen evidence of that in college students all the time. They clearly know their numbers, but there was this misconception that was never addressed when they were kids, and it can come up to bite us sometimes. And when we can, we want to address misconceptions. So drawing that out is kind of a nice thing. A game you can kind of do with kids with this is get a long piece of paper, like a legal size paper, and cut it in half the long way. So you end up with a kind of long, skinny piece of paper like that. And then you fold it accordion style. And so then what you can do is write facts about all the different place values. And then you can unfold it. You can tape a bunch of them together. So you can make this accordion number system to play with, which is kind of cute. It's fun math project. Does that mean? Somebody? That's you? Okay. All right. Am I recording, I think? Got sound, got video, I think. All right. So that's kind of a cute thing about our number system. We do have this balance. Does everybody in the world use a period for the decimal separator? whole number from fractional numbers. Danielle's shaking her head no, you guys are thinking no since I asked the question, right? So yeah, they don't. Like in France, they use a comma. And so some countries, when they see us putting commas all over the place, go, what the hell are you doing? There's only one of those. Right? They use spaces to separate the groups of three. Okay, so people express that different. It used to be early on with decimals that if I had a number like 12.34, instead of putting the decimal point separating the whole number part from the fractional part, the proper fraction part, they would circle the whole number part, identifying that balance in the middle that the ones give us. Tens on one side, tenths on the other. Right. Or they maybe underline the ones position so we could tell what it was. So it took a while for the way we write decimals today to evolve. And it's somewhere between, I think, 200 and 300 years that we've been working on this. And it's fairly standard throughout the world, but it's not totally standard still. Some countries say, no, we like the common better than the period. Sorry. That's okay. Yeah.
What do they use when they have like
A big number?
100,000?
They space the numbers out. So for bigger numbers, somebody in another country might, like suppose I had 1 million something. They would write a 1, put a little space, another little space, and then when it was time for the decimal, they put a comma in, and then whatever the decimal part was. And so we would write that as 1,234,052. So it turns out writing numerals isn't standard throughout the world. A lot of countries use the same set of symbols, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and some countries don't. Right? They have different way of writing their numerals. And some countries just don't use the same separators as we do. That's okay. Not too hard to translate those.
When it's circling, like spacing it, if another country looked at, like when they wrote down for a certain survey or something, it's confusing.
It's life. Everybody believes they're right. It's all a matter of opinion. There's no best way to do this kind of stuff. Sometimes there is, sometimes there isn't. In this case, there's no best way to write numbers. There's just different ways.
So it's like a math political correctness.
Yeah, well, it's like the same thing. We like to use our little carrying algorithm for multiplication. Other countries like to use their cute little lattice. You know, they're both great. They both have pros and cons. Some countries do short division, we do long division. Some countries do equal addition, subtraction, we do a borrowing for subtraction. It's a matter of choice, preference. Okay. All right, so basics of decimals, place values. Reminder, decimal really is our whole number system. What we're talking about now are decimal fractions. Usually when we're talking about fractions, we start with proper fractions. Proper fractions tend to be greater than 0, but less than 1. Forgetting about negative numbers for a little bit. And so when somebody gives me a decimal like 0.23, remember the saying 0.23 or 0.23 is slang. It's not the proper way to read it. The proper way to read it is to identify the place value, tenths, hundredths. So this must be 23 hundredths. So that's how stating it as a fraction, identifying the place value is how we read it properly. Then we can reduce if necessary if we wanted to turn it into a regular fraction. Turns out this one doesn't reduce. Now, that idea even extends to non-proper fractions, improper fractions. So, for example, 2.17 could be read in a couple of ways. I could read it as 2 and 17 hundredths. Or if I take, that's a 17 by the way right there, if I kind of take a different perspective from the previous problem I just did, for the previous problem I did, I identified that's tenths, that's hundredths, right? And then looking back, once I identified the denominator, I just wrote the numerals for the numerator, forgetting about the decimal. Well, why can't I do that here? Why can't I say this is just then 217 hundredths? So we have two ways to deal with improper fractions from decimals, the mixed number version and the improper fraction version. You want to see the connection between those two? And then this one I picked, so I didn't have to reduce it, but sometimes if we wanted to have it as a fraction, we might reduce it, if that makes sense to do so. I'm looking for triple values everywhere. Okay, so let's see, decimal basics. Excuse me, other thing we need to talk about is modeling decimals. So a couple of things to think of. A decimal, in this case, I'm talking about decimal fractions, right? Not just whole numbers. And so with the idea of fractions, put that in there. What were our models for fractions? Well, part of a whole is a big one. And we actually had two versions of part of a whole. Does anybody remember the two different versions of part of a whole? So we're reviewing fractions for a sec. It was part of a whole area or part of a whole group. And we can do the same for decimals. Let's see, what were some of our other models for fractions? Anybody else remember?
We have groups of, groups in.
Groups in would be division, so part of a whole group is what I've added up there.
Tracking.
Well, forget about adding and subtracting, just what does it mean to be a decimal fraction? Well, it's the same thing as what it means to be a regular fraction. So our different models were part of a whole area, part of a whole group, a ratio, like 2 boys versus 3 girls.
That number right there.
We have the number line model. Actual division. And those were the 5. I went over, the book gave one more. Does anyone remember the one the book gave that I didn't go over in class? The book also went over probability. So take a little closer look at probability this time. So I can use any of those to model a decimal. I'm going to go for part of a whole group / area idea. And to do that, I'm going to bring up one of my online toys. So on our announcements page, on our home page, I have an online manipulatives. And there's a National Library of virtual, what's supposed to say of now? Or, fix that, virtual manipulatives. It runs on Java, and sometimes Java can be fussy in different browsers. So a few minutes ago, I couldn't get it to run in Chrome, I couldn't get it to run in Firefox, but finally Internet Explorer ran it. So that can be a pain in the butt.
Which one was it?
Oh, so I went in, so here's the National Manipulatives Library, page 1. I went in under number and operation, and then I was looking at the base block decimals. And we played with the base 10 blocks before. This is a virtual way to play with them again. What I get to do this time is I get to choose one of the blocks to be a fractional unit. So before, we let these little guys over here be the 1s, and then the 10s, 100s, and 1000s. But we can just reinterpret those. we could have these little ones be tenths. And then these long ones would be ones, and these would be tens, and so on. We could decide to do it a little different. We could decide that these little guys are going to be hundredths, so these would be tenths, and then the big ones would be, let's see, is there a way to put one in there? Oh, this is giving me problems to solve. That is not what I wanted. Click the wrong one. Get that. So, pick a different one.
It's an interesting way to look at it, though.
Yeah, so we can use, so I'm going to grab the base 10 blocks and I'll let you guys play in just a minute. I don't want operations. I just want to share this. Just base blocks. Oh, come on. There you go.
It just keeps trying to, if your Java's not totally up there, it keeps
Run this time. There we go. Okay. So I just switched which one I grabbed. So this time I decided to grab just the base blocks. That's what I meant to grab. And so here I can choose which one I want to be tenths or hundredths. So I think I'm going to go for these guys right here are going to be my tenths. These guys here are going to be my hundredths, and those guys are going to be my whole numbers. And so these guys here will be my tens. So I just represented 12.12, so 12.34. And the same rules apply before for trading in and breaking down. So I could take one of these guys over here, drop it in that column, it'll break it up for me. And I can highlight a group of them. Highlight two.
Would it do the same?
There it is. And I can regroup them and put them back. Yes, awesome. Oh well. Sometimes it works well and sometimes it doesn't. Today it's not working well. But you get the idea. So my online manipulators are getting a little old and cranky. The physical ones are much more fun. Why would you bother with these except to share them in the video? Okay, so let's get back here. So we're going to look at part of a whole area of a group for decimal fractions. And so I brought some graph paper that we'll play around with, and that's nice to use here. So let's get my graph paper out. Black. So let's see. Oh, it's not tracking so well. Start right there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5. And so let's just say for now, we're going to let this right here be one whole. Share some of this graph paper with y'all. Bottom slightly better quality. Top. Grab one and pass it around. So what's the small, if that's one whole, what's the smallest decimal value I can represent here?
How many squares?
1/100.
It's 10 by 10. 1/100th would be the smallest. So then this guy right there would be 1/100th in the shorthand, in fraction notation, 1/100th. And so when you're teaching decimals, you are going to say slang all of the time. And you're going to try and fight yourself over it. You're going to say 0.01. But as often as possible, especially when you're new to this, when kids are new to this, you want to read it properly as 1/100th. And then, so for example, color. If I grab this region right here, that region right there would represent 1/10. And I want to read that properly. So it's a shorthand for 1/10. Now, when you're doing these with kids, it's very likely that they're going to be more familiar with decimals than fractions, but the curriculum usually does more with fractions early on and then starts slowly introducing decimals to it. So you should be okay with that. Now, what's a benefit of decimal fractions versus regular fractions? Tell me a few benefits you think of. Yeah, adding and subtracting are really easy because you have common denominators are just a matter of place value.
You
So
can,
that's nice.
you can define some numbers a bit more easily.
Some numbers can be defined pretty easy, yeah, especially with a 10 by 10 grid in front of you, you can easily draw them out. Okay.
But some can be a bit harder to.
Yeah. Are decimals maybe easier to order? Can be. You know, so for example, somebody might give me 0.013 versus 0.006, and I want to decide which one's the bigger one. Well, it's just a matter of reading them properly, right? They both happen to have the same place value, so 13 thousandths versus 6 thousandths. Which one's bigger? 13 thousandths. If I gave a different set, stick with the 13. What's my dilemma here? 13 thousandths versus 6 hundredths. Might not be obvious to some kids. What can we do to fix it?
Add another 0.
Put another 0 on here. And so now we have 13 thousandths versus 60 thousandths. Now is it pretty obvious which one's bigger? That's not too bad. It's kind of the same way it works with whole numbers as long as we line up each place value to see which one's bigger. One has a bigger place on the further down on the right, it's going to be bigger. Now with fractions, it's a lot harder. Like what's bigger, 9/40ths or 1/3 off the top of your head? Oops. 1/3? Okay, was that instant knowledge to you? Or do you have to think about it a little bit?
It just seemed like it was.
Just seemed like it was?
Yeah.
Yeah, so we could double check. One quick way to double check these guys is to cross multiply. 3 times 9 is 27. 4 times 1 is 40. So that's basically finding a common denominator of 120. So 27 versus 40, that means this guy is bigger. It's a little more work to judge if two fractions are alike or different. Sometimes I can just look and have a good idea. 1/3 is bigger. Had I put them on the other side of them, might I like tricked you thinking, oh, maybe 1/3 is smaller? Maybe no.
It was 3
Danielle's
parts.
not.
3 parts versus 40 parts is what I was thinking.
Okay.
But also you could just think, well, add one more to the 40, then that's 1/4 and 1/3 is bigger than 1/4. No.
But what if it was like, let's go with page 13/40ths versus 1/3. Which one's bigger? Let's see, multiply over, that's a 40. 13/40. Multiply over there, that's a 39. So it looks like 1/3 is still bigger.
So until you hit 1430, it's 1/3.
Because that would be 120 for both of those, is what I'm calculating there. For comparison. Yeah, so 1/3 is still bigger. So sometimes you can look at fractions and say, yeah, maybe, yeah, I got that one. And other times it's like, oh, I better figure it out. Fractions are nice, but they are a pain sometimes. The nice thing about decimals is the denominator just flows with powers of 10. We have our 1/10ths. We have our 100ths. We have our 1000ths. We have our 1 10,000ths. And we have our 1 100,000th. So as long as we know our whole number place values, we know our decimal place values. How do you know that? All right, a couple other quick things, and I'm going to shut up and let you guys play. Quick overview of addition and subtraction. We'll come back and play with this later. What does addition mean to us?
Combine and count.
Combine and count. Thank you. Combine and count. And so when I'm working with decimals like 0.6 and 0.13, combine and count. Well, at the moment I have 6/10 and 1300ths. They feel kind of different. What could I do to make them more similar?
Add the 0 to it.
Put the 0, yeah, I can just put a 0 there. And so now I have, 60/100ths and 1300ths, they're both hundredths. Nice thing about that is when we rewrite it stacked, if we line up the decimal places, then we're guaranteed that place values are the same. Because we have our hundredths lined up, and our tenths lined up, and so on. So it's pretty straightforward. We get a common denominator instantly by just aligning the decimal point. So altogether, I think I have 7300ths. And we can show that with the toys pretty easy, and you guys are going to do some activities just double checking that. What does subtraction mean? Take away, or what's the other popular one?
Less than.
Yeah, or just compare. Sometimes we call that comparison the difference. So if I wanted to do, for example, 0.6 minus 0.13, I can grab my graph paper again, and I can draw a picture of that. Graph paper is. And you should notice the graph paper I gave you already has 10 marks kind of delineated on there. Makes it nice. Copy of that sucker. Draw right over it. That's much better. Good stuff. So then I can draw in 1, 2, 3, 4, 5, 6/10, 1/10, right, reading place value, and 1, 2, 300ths. And so either I could go for the takeaway here, or I could go for the comparison. Since I drew both pictures, I set myself up to do the comparison. So then I can say, okay, let's match them up for the comparison. Let's see, this guy here goes with that guy there. And then this guy goes with that one, and this one gets paired with that one, and this one gets paired with that one. And so then I can see how they're different. Let's see if I can highlight the difference. So the difference appears to be this group of stuff. So I'm pretty sure from my comparison that the difference is what? 1, 2, 3, 4 tenths and 7/100ths. 4 tenths and 7/100ths. If I had the physical toys with me, what else would I have to do to demonstrate that here, maybe?
Cut up one of the blocks.
Yeah, I'd have to do a trade-in, right? I'd have to trade in. There we go. Trade 1/10 for 10/100ths to make that happen, right? So we'll show kids that, and it's just like borrowing was before. What's important, like with addition, when I do my algorithm instead of my model? So back
The
here.
algorithm is lining up the decimals.
Yeah, so the algorithm here was line up the decimal, add as usual. The algorithm here is the same thing. Line up the decimal, 0.6 minus 0.13. It makes us feel better to put that 0 in up there. And then when I actually go to do the work here, I realize I have to borrow one of those tenths. So there's my 10/100ths, right? So that's my trading in is borrowing. And so I have 7/100ths left, and there's my 4/10ths remaining. All right, so that's subtraction. Multiplication. What does that mean? Multiplication models.
Area model.
That's the area model. That's a popular one. I love that one. And there's another. What was the next most popular one? Groups of. The other one. Now, multiplication is pretty easy, but drawing pictures gets harder. And so we have to be careful what we choose for problems to draw pictures. So I'm just going to stick with tenths to draw pictures. And so suppose I had 0.2 times 0.3. So I want to model that. So one option, if I go with the area, I would have to draw an area. And usually when I do area, I like to call them base and height. We talked about that with you before. Mainly because when I call them length and width, I get confused about which should be which. So I could draw a base of 0.2 and a height of 0.3, and then see if we can come up with an answer. We'll do that in a second. And the other option is to try and draw what is 2/10 of a group of 3/10. And so then I have to show 3/10 and then try to identify what is 2/10 of that 3/10. And we tried drawing that before in class. So let's give that a shot. We're going to need our graph paper to do this. I'm going to go for the area first. Graph paper. Let's copy this rectangle right there. So again, I'm trying to draw an area with a base of 2/10 and a height of 3/10. And so I'm going to go across my bottom here. And if this from here to here is one hole, then that right there is my 2/10. And if this from here to here is one hole, then that right there would be 3/10. So that means I want the region that is 2/10 by 3/10. So I want to identify that region right there. Now, one interesting thing when we go into multiplication, multiplication means we're going from linear measurements to an area measurement. So that means this whole thing is 1 square unit. So then the question is, what part of that square unit do I have here? Well, how many little pieces do I have of this square unit? I have 6 little pieces. How many total pieces are there? There's 100. And so thinking about place value, I've just found the answer is 6/100. Okay. And so then we repeat that a few times with kids with different problems. And to draw it, if you try to do anything but tenths times tenths, the drawings are too hard to possibly draw. So we just stick with that. We do a whole bunch of these. And then what we try to do is we try to say, okay, can we develop a procedure, some rules, to get us from here to there? How do we make that connection there? Let's see, does anybody see any obvious things?
Most funny, just like 20 by 30, except you're moving the decimal with zeros.
Kind of like 20 times 30. Also, 2 times 3 is in there, right? 2 times 3 is 6. So it's a matter of identifying the right place value. Okay, so let's see. What's this number right here?
0.2.
And it's not 0.2. Well, it kind of is. That's slang though.
2/10.
Oh, that's 2/10, right? Okay. And then what is this guy right here?
3/10.
That's really 3/10. And then we might remember that, well, that means we have a 2 by 3 section out of a region that's 10 by 10. And so there's our 6/100 that way. Now, when we have multi-digit numbers, how do we like to write down that multiplication? Like if I gave you 16 times 23 and you didn't have a calculator, what are you going to do? Are you going to write 16 times 23 like that and get me an answer? No, you're going to do what? You're going to stack them, right? Okay. So you'd write it as 16 times 23. Okay, so we really do have a multi-digit problem here, 0.3 times 0.2. Now, my decimals happen to line up. I don't know if that's important yet, just because of the numbers I chose. Okay, well, I know 2 times 3 is 6. That's kind of cool. Does it make sense to drop the decimal point down? Is my answer 6/10 according to my picture? Definitely not. Okay, so I can't follow the same rules as addition. Agreed? Doesn't work here. But I can make this observation. What's this number read properly? It's 3/10, right? So there's tenths there. And this guy is a tenth also, 2/10. And since multiplication is area, 10 by 10 gives me 100. What that means is I have to account for every decimal fraction place in my numbers. And the more you play around with that, the more that'll pop out. So we'll do another example of that in a second. So that means I have 2 decimal places here, so my answer needs to have 2 decimal places. And that's where the decimal point's going to have to go. So that's our algorithm. We need to do a little more work to justify it. So count decimal fraction places. All right, so let's try another one. How about, can you draw for me 0.4 times 0.6? So draw a picture of that using an area model. see what we get. All right, so 4 times 6 is definitely 24. We do have a 4 by 6 region here, so there's 24 of something going on in this picture. Yeah, and we know a hole, that's one hole going that way, is a 10 by 10 region. And so the decimal point naturally has to go right there. And so again, kind of getting at that, the number of decimal place values represented in the factors has to be in the answer. So you got a place value, place value, place value, place value. It's got to match up. So we do a bunch of pictures to show that. And remember, we got to stick with tenths times tenths to draw these pictures. Try drawing hundreds times tenths. It's a pain, but kids will get lost. This is hard enough. All right, let's see. What else do we need to do? Multiplication, division. What's division mean? Groups in. And that's a pretty good one. Repeated subtraction can work for some of them too. And with division, to model it, you got to kind of pick problems that work out limits, otherwise it gets too messy. Remember how sometimes our fraction divisions pictures got very messy, got painful? Yeah, so you have to choose very, very carefully. So I'm going to choose pretty carefully here. I'm going to say I'm going to try 0.21 divided by 0.7. And so if groups in as our interpretation, what is this problem telling me to do? What's the question that's being asked here?
How many groups are 7 tenths or?
Oop, that's not what I want to do. I want to look in 700s, sorry. There we go. We'll try the other one in a minute, it's a little harder. How many groups of 700s are in 2100s? And so that's one we can draw pretty easily. So I can draw, it's not quite lined up close enough. So there's my 2100s, and then in there I'm looking for groups of 700s. So 1, 2, 3, 4, 5, 6, 7. There's 1, 1, 2, 3, 4, 5, 6, 7. There's 2, 1, 2, 3, 4, 5, 6, 7. There's 3. question. Was that any different than 21 divided by 7? Couldn't I easily interpret this picture as that? We looked at base 10 blocks before. That's not much different. So really here I ended up taking 7 into 21 when I'm counting pieces. Okay. Versus 0.21 divided by 0.07. But now this is slightly different. So this one I definitely call division symbol. Anybody remember what I call this box here? A slightly different name for that. It goes into box. So I want to know how many times 7 goes into 21, right? We read it backwards to solve it. And this involves what we call the division algorithm. The division algorithm. And the division algorithm depends on counting. That's important. To do this problem physically, I had to count. Those are my little dots I drew up there in my picture. I had to count to solve this. Let's see. If I'm counting, what kinds of numbers am I working with? Yeah, the whole numbers, counting numbers. Okay. So the bottom line is the division algorithm really works best if we're working with whole numbers. And so what we want is we want to be counting by whole numbers. So this guy out here, we want to be a whole number for division to work. And generally, it's not just a whole number, really, it's a counting number. Because I'm not going to have a 0 there. So technically, it's a counting number.
And negative numbers count as counting numbers, right?
No, counting numbers are 1, 2, 3, 4, 5. The opposites of the counting numbers are part of the numbers we call the integers.
So then you couldn't do that with negative?
You could, but then you have to have rules for dealing with the negative part, which we developed separate rules for that. Okay. So otherwise, it doesn't matter whether they're positive or negative, the division algorithm works the same way. But the division algorithm depends on your divisor being a whole number. And so here's the trick on that, which you guys know about. I just want to justify a little bit here. So the division algorithm relies on counting. Counting means we're using whole numbers, so our divisor has to be a whole number. Can you try to count with fractions or decimals? Yeah, but you have to focus very, very, very hard to keep it straight. So, as far as division goes, I started off with 0.21 divided by 0.07. That can also be written with the goes into, 0.07 divided by, or goes into, excuse me, 0.21. What's other ways I could write this down? Kelly?
Fraction?
Yeah, it's a fraction. I could write it as 0.21 over 0.07. Now, what are legal things to do to fractions to keep them the same value but looking different?
Wouldn't it, if it was divided, wouldn't it be the 7 over
Multiply by 1.
Multiplying by 1. And we do that by doing things like multiplying top and bottom by the same thing. Right? So for example, I could choose to multiply top and bottom by 10. That's the same as multiplying by 1, because 10 over 10 is 1. That lets me rewrite this. So 0.21 over 0.07 is the same as 2.1 over 0.7. I could do that again. I can multiply top and bottom by 10. So that means this is the same as 21 over 7. So from what I know about fractions, I know that I can multiply by some power of 10. Would have been quicker to multiply by 100, but that's okay. So that I can make the divisor a whole number. And so that's the goal when we're doing division. What we want to do is we want to look at this and say, okay, let's make the divisor a whole number. So we want to move the decimal point there. That's multiplying by 100 to do that. So that means I have to take the numerator and multiply it by 100 too, so the decimal has to go there. And what that tells me is where the decimal has to go in the answer. And then I just divide like normal. I don't have to do anything here. So it just tells me where the decimal goes in the answer. And so what we want to do is we play around a little bit with some simple problems, just talking about groups in, goes into. And eventually we realize that, oh, we're always counting when we do that, which means we better make the divisor a counting number. Which means we have to adjust the dividend so that we know where the decimal goes in the answer. Because whatever we multiply the top by, or the bottom by, excuse me, we have to do the same thing for the top to keep them equal along the way. That's why when we divide by with decimals, we make sure it doesn't matter what the dividend is. The divisor is important. We adjust it first. So even if I was doing a problem like 0.6, and that's going into 1.236. All that matters is that I make the divisor a whole number. The dividend just follows along. So this should be the same as 6 goes into 12.36. Doesn't matter that this is not a whole number, the dividend, as long as I know where the decimal goes in the answer. And it's all about counting, and I count with counting numbers. 2.6. All right, so I jump in there. Yeah, 6 doesn't go into 1, it goes into 12 twice. 2 times 6 is 12. Well, that's nice. And then I get 0, bring down the 3. How many times, and I don't even actually need the decimal here anymore, because I know where it goes up above. How many times does 6 go into 3?
5 times.
0.
0 times, yeah. So you got to be careful there. It goes in 0 times. I can't do anything there. I got to bring down the 6. And you got to keep track of those places. How many times does 6 go into 36? 6. Yeah, now the 6 goes there. Now, 6 times 6 is 36. Subtract and I get a 0. I could have screwed that up because a lot of people are going to write 2.6 instead of 2.06. How do we check to see if we're right? Besides asking a calculator. Yeah, multiply. Okay, so then we take the 2.06 and we multiply that by 6. And we learned earlier it doesn't matter where the decimal plate is yet. 6 times 6 is 36. 6 times 0 is 6 plus 3. Sorry, 0 plus 3 is 3. 6 times 2 is 12. There's 2 decimals, fractions in the factors, so there's 2 in the answer. So there's my 12.36 that I have here. Did I get it right? All right, so that's enough for that stuff. We'll review some of this stuff next time and go into a little more detail on a few things. Let's take a look at activities. So on the website, I got a list of activities we need to do. Let's take a quick look at those. Hi, Debbie.
Hello.
Can you hear me?
Yes, I can.
Uh-oh. It says I have volume.
Yeah, I can hear you.
Oh, you can't hear me. She's nodding her head. Okay. Cool. I think I must have mine muted. Oh yeah. Say something now.
Okay.
Oh, there you go. I had my mic muted. Darn it. Oops. Well, at least you could hear me. That's
Yes.
important. Okay. So let's see. Activities here on the home page. Blow that up. So we're in chapter 7, and so the ones I wanted you to do are 1, 3, 5, 6, 9, and 10. Let's take a quick look at those. I have them somewhere here on the computer. And Debbie, I emailed you about the in-class exam. I'm not done grading yet.
Okay.
So take a look at that, and hopefully by tomorrow I'll get back to you about the take-home.
Okay.
Let's see, activities. There. chapter 7, that's it. Aha, here we go. All right, so 1. So number 1 is kind of like thinking about base 10 blocks. We have a rod here that has 10 units in it. And if the rod is a whole, then what is the shaded part as a fraction and a decimal? So this, what's that?
Thought we went over this part already.
Yeah, just going over what needs to be done here. And then it breaks into playing with patterns on the next page, but still, this time we have the whole square as one whole. Right? So we're changing what the meaning of the base 10 blocks is. And so we want to be careful there. So this is just getting used to representing decimals. And so you want to be super careful with kids in class. It's usually not a good idea to switch between this being a whole and then this being a whole in the same day at first, because that's going to blow some minds. Right? We want to be consistent in a given day. We're skipping number 2. Number 3 is a game I want you to play with somebody else. And so you can make your own set of dice to do it. You can roll a regular die and just use the numbers 1 through 6. One die roll will represent the tens. The other die roll will represent the hundreds value, or tenths, sorry, and hundredths values. And it's basically going back and forth. And the first one to roll enough, 2 dice at a time, to fill up a flat is the winner. And so it's practice adding decimals. Okay, so this is a fun activity you would do with kids that are learning decimals. They can each roll against each other one at a time. So they have to roll, write the number down. Next person rolls, they roll again, they add that, they shade it in on their picture, and then move on. So you can either play that with a classmate or with somebody outside of school, but I'd like to see a sheet of you messing around with that. Next one, we're skipping 4 and we are jumping to 5. So we kind of looked at 5 a little bit today in class. Those are the area model basically for decimals multiplication. And so that shouldn't be a big deal. The big deal about dealing with decimal multiplication is identify what's a whole unit after we multiply. Okay? So a whole unit here is one big 10 by 10 square. That's a whole. So we want to be careful reminding ourselves every time we do a fraction or a decimal multiplication, what does it mean to be a whole now? Okay. And so in this case, we're doing just tenths by tenths, so a whole is a 10 by 10 grid. And so we'll do that in 2 different ways. Here's the problem, you draw the picture. Here's the picture, what's the problem? Right, in the last part. So for sure, what I'd like you to work on right now and over the next couple of days are activities 1, 3, and 5. Those are the easy ones. And basically, it's like, what is a decimal representation with base 10 blocks? And what does it mean to multiply? Which again, we're relying on the area model. Let's see, what are the other things we're going to do? 1, 3, 5, or 6, 9, and 10. I don't think we're ready for those. 6, okay, you can start 6 if you want, but this is related to activity way back in chapter 3 that everybody had a hard time with. So feel free to get it started, but I want to talk about this in detail in class on Wednesday. 9 and 6, 9, and 10. So 9, I think, is division, if I remember right. Oh, 9 is repeating decimals, that's right. So that comes up in section 3 of the book. So far what we've covered is most of 7.1 and about 3/4 of 7.2 is what we've covered today so far. So you can put off 9 for a little while. And then 10, 9's quite a bit of work. Yeah, and then 10 is that one's actually pretty easy. It relates back to the whole idea of probability and percentages, which is going to work us into a future chapter. So that one's not going to be bad. But the 9 is a bit of work, and so is 6. So for now, we're going to dive into getting 1, 2, and 4 ready. Kelly, remember, you need a copy, right? So I can put that. So I would recommend, 1 is pretty straightforward. 3 would be a good one to do right now because you have a partner in the room and I have dice here. Or you could jump right into number 5. All right, and I am going to stop the recording, but I'm not going to close the session, Debbie, so
Okay.
push the right button. I think I just pushed that one.